So we'll return to this. So it turns out that if you just use parallel bonded material, discs and spheres, that you're not able to match both tension and compression, both tensile strength and compressive strength. What you do is you can match the tensile strength and then the compressive strength is too low. Okay. Now this is for a compact rock like granite. The compressive over tensile strength ratio of certain types of granite is like could be up to 30. Um, the ratios that we get with parallel bonded disc or spheres are on the order of 5 or 6. Okay. Um, After many years of research by myself and others, and I can show you all kinds of journal papers years back where people would do all these different things to try to do things to parallel bonded systems to make them get this much higher, compressive strength. We finally determined a way to do that, and it all has to do with having more interlock. Okay. Um, so if you can the problem here is that with a parallel bonded system, I think is shown here. Here's the issue. Um, Turns out that this flat jointed material, I developed that model to solve this problem. And here's the thinking behind it. So this would be two discs joined by a parallel bond where the cement is drawn as yellow, right? Um, and so that behaves as though it was an interface between those two discs, and it's elastic. As long as the bond is present, it really behaves like that. So it has this good interlock. But as soon as it breaks, the cement is removed, and the only thing you have now is just friction acting over that small area to try to maintain interlock, and that doesn't provide almost hardly any interlock. Okay. The idea with the flat joint is that notice that it still remains, that interface is still there. Conceptually, that interface is still there. Um, and so it maintains this interlock, okay, and the material holds itself together. The reason this matters, I'm trying to see if I have an example of this, is that let's just talk about this. So with the parallel bonded material, what you would do when you calibrate it is you first do a direct tension test and you choose the micro tensile strength so that you can match the macro tensile strength. Okay. And what you find when you do such a model is that all of the damage that you see in a direct tension test is micro tensile breakages, which means that the shear strength is not participating. The micro shear strength has nothing to do with the direct tensile strength. So that means now, and then what you do is you say, okay, now I'm going to do a UCS test on this material. Now you can't change the micro tensile strength. That's done. That's been fixed. So the only thing you have left is the micro shear strength. And so you do the most extreme case. Okay, if the micro shear strength is the parameter the only one that's going to help me get a high value of UCS, let's just do the extreme case. Let's set the micro shear strength to infinity. Okay, so you do that and you run a UCS test, and what you'll get is that the UCS will be 5 to 6 times bigger than the direct tensile strength. And when the thing fails in UCS, it all just fails by micro tensile failure because you set the micro shear strength infinite. And and so what's happening is that it starts to crack with these little tensile breakages all throughout the material. Like it cracks in one spot, then it cracks further away, then it cracks somewhere else. And you get this just this heterogeneous distribution of micro cracks, which is what happens in real rock as well. But then it localizes at one spot and you get this zoom, 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 and this axial split forms. Okay. And that's all just driven by microtensile failure. So there's nothing you can do anymore with that model to raise its UCS. When you have these these remaining interfaces that you get with a flat joint, what happens is that you calibrate to get a micro to the direct tension test, and what you find is it's the micro tensile strength that governs that, and so you choose the micro tensile strength again. But then what happens is when you start to do a UCS test, what you find is that you don't get this localization. You just get partial breakage of tensile cracks all throughout the system. And then in order for the thing to fail, there has to be some localization where these things participate so that you can get an axial split or a shear fracture that spans the specimen. That process of localization to create that requires a small number of micro shear failures to link these things up. Therefore, by choosing the micro shear strength, you can dial up the UCS to these relatively large numbers. And so that's why the flat jointed material can give you these high values of UCS relative to tensile strength. That's also why these Voronoi block materials can do the same thing, because the material during a UCS test is able to keep on taking lots of damage before it finally will fail. All right. So that's a solution to this problem of the UCS being too small relative to the tensile strength. And here's just a simple example that demonstrates this. This is the case for asphodierite. This is a very hard rock. This happens to be in the Swedish nuclear waste underground research laboratory, and we've been doing some work with them. And so this would be the really simple example, a bonded system. We identify particles above and below, and we slowly pull this apart, measuring stress and strain as we go. And here's the tensile strength test. It loads up and then it fails. And you can see this is the damage that's occurred at this point in the test. So, okay, so there's my tensile strength, 10 MPa. Then I take the same material and I squeeze it between platens to simulate a UCS test. And here you see you're going all the way up to 200 MPa. So there we've got this high ratio of compressive to tensile strength. And if we look, notice what you've got is the thickness of these are the cracks. These are broken elements. Remember, the flat joint in this case has 4 elements. Each flat joint interface has 4 elements, each of which can independently break. And so this is, each of those little elements is drawn here. So like right up here, there's only one of the 4 that's broken. So it's a very short break. And the thickness of these lines is proportional to the gap, the current gap of how much open that thing is. And so you can see once at the peak, we've gotten this big amount of opening going on here, and we have quite a bit of distributed damage before that. If you look in detail at this thing, this is what's happening right at the peak load. You're basically getting a localization to happen here, and then it's proceeding downward to break the system. In order for this to happen again, the black color is micro shear failure. So in order for this thing to localize and create that axial split, there has to be some micro shear failure. So that's the key thing that's allowing this thing to reach the peak, to begin to fail. So it's that micro shear strength that can be chosen to match the UCS. And if you look, it's a very sophisticated, complicated system. You know, this is just looking at early on in the test at some region. And if we zoom in on that and we look carefully, we can see, for example, here, these two guys are actually rotating a little bit when you load it. There's all kinds of micro rotations that occur when you load these things. And so that micro rotation now is causing tension on this side and compression on that side. And so you're getting this partial damage. If this was a parallel bonded contact, once the outer fiber reaches the tensile strength, the entire thing breaks and is removed. Whereas here, I get this distributed tensile breakage. It redistributes the load. It goes somewhere else. Here's another one that's beginning to fail. And so this is, again, the mechanism that we have in these flat jointed material, and we think that that's the proper mechanism. Basically, the grain boundaries are not just completely breaking, and they're clearly not just breaking and disappearing. Um, so the parallel bonded thing would probably be better for something like a sandstone than something like a compact rock like this. All right. Um, so that's the basic idea. And then here's a little bit more of a scheme to convince us that this makes sense. We're going to build two different bonded particle models. We're going to build the one on the right, which is using disks, and it's using flat joint contacts. And so remember, we can draw them in this fashion to actually see what mechanically that system looks like. Okay. Then it's also building a system that's this grain-based model. So if you recall, the grain-based model, close your eyes, looks like this here, where we take a collection of disks, we join them with parallel bonds, and then we overlay these joints on top. So we overlay a joint structure. And so inside of each one of these grains, there might be, might be 50 or more parallel bonds, all of which can break. So we call that a grain-based model. So let's compare both of these. So what's the difference here? This grain in the flat jointed thing is rigid, right? Because it's just a disk, it's a PFC particle, it doesn't deform. This grain is deformable and it's also breakable. Okay. There's an interface between the grains. In both cases, these things are deformable, they're breakable, and they can sustain partial damage. Okay. This model, of course, is much, much fewer particles than this one. Okay. So if you look at that grain-based material, the grain-based model is extremely realistic. This up here is the final state of a direct tension test. Okay, and you can see what's happened here is that this pink is microtensile failure, and you can see that a predominant fracture has grown across this specimen. There's been a little bit here and a little bit here, but they didn't go all the way across to make it fail. These are all microtensile cracks. If you look down here, forget about this line is irrelevant. If you look here, this is about halfway to the peak in a UCS test. And what you start seeing, and notice there's lots of partial damage along the grain boundaries, but you then also see these regions where the entire boundary is broken. That's what I've circled here. And then when you get near peak, again, these are all microtensile cracks. When you get near peak, what's triggering the failure here is you're getting these shear cracks, these black guys that are then going to end up linking up. These actually look a lot like this, looks like wing cracks from a sliding crack. This is actually a force chain plot right after the peak. And this force chain plot is using black and blue for compression and red for tension. But the thing that's interesting about it is you can see how this material is dilating as it's beginning to fail. This plot, it's like an indirect way of drawing this, okay? Because we're drawing all those force chains, and because the material is split apart here, there's no force chains showing there. So it sort of pulls out the aspect of the fact that this is basically breaking into a bunch of parallel columns. So this is actually what we believe is the real mechanism of rock. This is also, this grain-based model was set up to have infinite strength inside the grains. So even without grain breakage, we're getting the very good calibrated response similar to something like a granite or a diorite. Okay. Now let's look at the flat jointed material for that same sort of a thing. This is Castlegate sandstone. This is the cross section. You can see the length scale here. The pink is basically void space between the grains. Here is a flat jointed material that has the disc size at the same scale as the grain size of this Castlegate sandstone. Obviously, this is a much simplified representation of this, but let's just see what we can get with it, okay? This, by the way, is the work that I did for BP, where we looked at perforation damage. Okay, so the first part of that work was to see that I had just developed the flat jointed material, so we wanted to see how good does it behave. And so forget about this. Let's just look at the right side. I pardon you. This is a poor curve. We're plotting axial stress, axial strain. Here's the 0 point, and the solid curves are real lab data. And so, for example, this is the unconfined case is black. So the material stiffens a little. It's closing up its pores. It's linear. It reaches a peak and it brittly fails. Then we go to the pink curve. That's 2.4 MPa confinement. And notice that it's stiffer and stronger. And then we go to the 5, you can see as you increase the confinement for this material, you're increasing its strength and you're increasing its stiffness. The dotted lines are the PFC material subjected to the same confinement conditions. And what we're seeing here is the PFC material, it has the same slope because we don't have any initial cracks in this system. It's all well connected for this model. But notice how the strengths, we're getting about the same strength increases with confinement as we were for the Castlegate sandstone, okay? Then we take this thing and we do a direct tension test on it, and we can see we're getting a single fracture like we should. We're getting a very brittle. We're seeing this snapback in the stress in the tension test because the way in this model that we were measuring axial stress was by putting a circular measurement region in here. And that measurement region was in the middle. And just think about what happens there. The stress is tension, tension, tension in the middle. And as it starts, once it starts to break, this middle region relieves its stress and not just its stress. So that causes the stress to drop, but we're also measuring strain in that region. And so that thing actually begins, the strain is tensile, tensile, tensile. And then in this region, once this fails, the strain starts relieving itself. And so that's why this thing is kicking back. If we were just measuring strain based on distance between the walls, then this would not be able to go negative. It would not go backwards. It would keep going forwards. Okay. Here's a fracture toughness test where we put in a crack to begin with. We just deleted contacts along a line to say that's an initial crack. We pull it. We get the breakage. Notice this one. This stress here is 1.3 MPa. If we machined in the crack, the stress it fails at is lower. You can compute that. You can turn that into a fracture toughness. There it is. We do an unconfined compression test. Here's all the damage we see. 18 MPa. We do a confined compression test. There's the higher thing. Notice you're getting these shear band-like regions in here. Notice the blue, that's the micro shear failure. You're shutting down the ability for the thing to axial split in tension. So therefore, it ends up forming these shear bands. This is showing that we have axial splitting during an unconfined compression test. This is the displacement field of the macroscopic specimen, and those little arrows are the displacement arrows of each ball, and you can see very clearly that this part is popping out and this part is popping out, so it's actually splitting on the sides. The other interesting, powerful thing is there's all kinds of complicated stuff going on inside the material. This is the damage, and this again is after the peak. And what you're seeing is very complex damage in here. You're seeing partially broken things. Again, thickness is proportional to the amount of opening. And so you're seeing these regions that have fully failed, these edges of the boundaries of the grains, right? The same sort of a thing happens if you do the bonded Voronoi grains, We've seen this one as kind of a funny slide before, where you're getting that axial splitting. Returning to the flat jointed material, now if you do test with some confinement on it, what you're getting in the specimen is a localization, which is at the macro scale is a shear fracture, which is what you expect to get when you when you do a triaxial test with confinement. Um, this is looking at just the material outside of the shear fracture region, right? And then this is looking at the material inside the shear fracture region. And you can see all of the how it's moving, it's breaking apart. These colors represent what we call fragments. So these two guys can reach each other if you start at a grain and you go to an if there's any existing bonded elements, you go to the next one and you go to the next one. So this guy has fully broken free from the system. Again, the blue, there's all this micro shear failure. So this is the detailed internal microstructure inside the shear band, which, there's all kinds of information in here about how that's failing. This is another way of looking at that same thing. This is the fragments that it has broken into. And then this is the same system, but now we're just looking at the basically the broken bonds, the broken elements. And again, thickness is proportional to the magnitude of how far I'm at the current point, how much they're open. So you can see there's all kinds of partial damage in here, but the main deformation is happening where these guys are bigger. All right. This is on the left, unconfined tests. These this is in the post-peak region, and again, you can see this is right at the peak. And then if you continue to apply strain, so the stress has dropped almost to zero, you can see how it's breaking up into these axially aligned columns. And then if you do the same material, but you apply confinement, now you're getting this shear fracture. So the stress strain curve looks like this, has this residual value. So this peak, at the peak here, just past the peak, this is what the system looks like. It's just beginning to form a shear band. If you keep applying more axial strain, it drops down and comes to a residual value, and that's because these shear bands are now fully formed. And once they're fully formed, we have a kinematic mechanism where we have these fractures with friction on them effectively. And so that's now this residual system. And so that's why this thing goes down and then reaches this residual value. If you apply more confinement, you get the same type of behavior, but the point A and the point B are higher. Okay, so this seems to be a very good representation of the steps that are going on in a rock as you load it. Okay, the last thing I will say, we do the same thing with 3D models where we have spherical particles in a cylinder and we put the flat joint model in there. And what we see is we basically see all the same types of behavior, except I've never been able to clearly detect shear bands in that 3D material. And now it may be that it's hard to find them. They don't pop out when you just make these plots here. But I don't know. That's an open issue. In the 3D flat jointed material, you basically get distributed damage of pencil cracks throughout the material. And then once you get near the peak, you get a small number of shear cracks that form and the specimen then will fail. So that's the flat jointed material. So this is a demonstration of the fact that you can go and build a grain-based material and really get in detail great behavior. If you do a grain-based material with no breakage, you're basically getting the similar type of response with a flat jointed material, which of course has far fewer particles that are required to do it. Okay. Just a few other things to show here. Here is we wanted to see if we could construct a rock that was anisotropic. that was transversely anisotropic. So we take and we bond these things together. We put in these joints by means of the smooth joints, and then we do UCS tests that are oriented different angles with respect to this. So this test is loading this way, this test is loading this way. It's at a different angle with respect to the all those little joints that are in there. We go uh, and we make those interfaces softer and weaker than the layer material, right? And then we see these different failure mechanisms. When it's at an angle, when you reach the peak, it's failing because you're triggering sliding along these interfaces. When it's like this, you don't get sliding. It's just the intact part of the system that has to fail. The result then is that we get the uh, variation of both. This is modulus with loading angle. So when it's loaded this way, it has a high modulus. But now when it's loaded this way, since these interfaces are softer, you're measuring that stiffness. And this is then comparing this with lab data for this particular argillite. So that's the modulus variation, but you're also getting the same sort of strength variation. So this is the UCS versus the loading angle. And you basically get this. You can build simple theoretical models of these things, and you see this same sort of a curve. You basically, once you get at a 45-degree angle here, you start getting failure along the interfaces, that just makes it weaker. But then when you're like this and like this, you're getting failure on the impact, which makes it stronger. And so this seems to, again, make sense. So we're putting in the anisotropy. Now if you're doing like a shale or something, you have this anisotropy, but these things are super close together. I don't know how to do that with a bonded system. So this is a little bit of a it's a demonstration that the general idea makes sense, but we wouldn't really have enough resolution to make it anisotropic with where the layers are so close. This is just an example of some work before where we put in basically suction forces at the contacts, and we basically link that to the amount of saturation in the system by means of two-phase flow theory. And so then what you can do is you can take that system and you can start drying it out. And as you start drying it out, you start increasing the suction. And so that's what we're seeing here. And so as we take a system of saturation from 0.97 and we reduce the saturation a little bit, that increases the suction. And what you then see is this evolution where it begins to fail at these tensile breakages and the boundary condition is fully fixed all around the boundary. So you've got this shrinking material fully fixed on the boundary. It's sucking itself in, and that then localizes, and then those localizations grow and eventually go across the whole thing. This is similar to like desiccation cracking of like a clay. So if I speed things up, you can see they're initiating, then they're interacting, and they're forming something like this. So that was some work just showing that, adding like a saturation type concept, a saturated material. This is this work where we were modeling, again, a stope in a deep underground mine in South Africa. And what we did is we used a PFC region in the tip of the stope, and we had that embedded in a much larger continuum grid. These stresses are very high. You can see that sigma y is 100 MPa, sigma x is 60 MPa. And this is this coupling scheme whereby we basically create a bonded system in this region of space. We then identify the boundary particles, and then we basically map each boundary particle into the edge of an element. And then what happens is the forces acting on these boundary particles get sent as traction boundaries to the continuum grid. And meanwhile, the deformation of the edges of these zones is imposed by these boundary particles. So effectively, these boundary particles are glued to the surfaces. So you build a big grid, you delete all the zones in the region where you're going to put the PFC material, and then you couple this. So every time you take a time step in one code, you take a time step in the other code, and they're exchanging information across the boundary. Um, this is now part of PFC. This was done back in 2012. This is part of PFC now. It's built in so that you can couple PFC with Black 3D. And we do that when we want to look at like damage around an excavation boundary. And this is just again showing as here's the PFC region, there's the broken bonds, and here's the system in equilibrium when the stope is 18.5 meters long, then we carve out some more. And as we do, we start seeing the formation of a new shear band. So this is a strain softening constitutive model that's in the Continuum code. And this is just pointing out where the coupling is making sense. We're getting a nice clean thing where the shear band is going from one representation into another. And this shear band in here, of course, you could use to study in detail what's going on in a shear band. Okay. All right. Conclusions. I would argue that this type of modeling is still, I would argue, in an early phase of development, meaning that we're just beginning to kind of have this different models for different types of rock. Really, what we still are typically doing is we're saying, oh, here's a rock, and here's what its tensile strength is, and here's what its UCS and modulus are, and we go and we create a microstructure, and then we calibrate its micro properties to match that. We're just now beginning to like build, different sorts of contact models, different sorts of microstructures, say to like be a sandstone for a porous rock versus like a granite where it's well connected. Okay. There's a whole entire talk about this perforation damage work that I did for BP originally, and I'm not going to go through that talk here. Instead, I'm going to just do a very, very brief summary on the next 5 slides of that work. That work was done with 2D flat jointed material. And so as if you have a sandstone and you basically have a borehole in there and you apply these high stresses to this on the boundary of this, you start getting damage and eventually the hole will collapse. And the damage, if you look closely, notice the length scale, 700 microns. Okay, this was work done by Professor Hameson at University of Wisconsin-Madison some years ago. So here's table rock sandstone. And notice what you're getting is you're getting this swarm of broken material right near, very close to the borehole wall. And that's consisting of both breakages along the grain boundaries and the grains themselves. You can see clearly the grains are also splitting in this system. And then what happens is if you, where's the length scale? 1 millimeter here. If you zoom back a little bit, at this scale, you start to see these fractures form and you start to see these fragments of broken material. If there's like fluid flowing in here, these tend to then can get carried away. Okay. And then this process will end up producing, it eventually forms a stable configuration and they look like this. They call these things breakouts. All right. This is the modeling that was done for that situation. This is modeling a thick-walled cylinder test where you take a cylinder of rock, you drill a hole in the middle of it. This is looking down on the cylinder. You take a cylinder of rock, you drill a hole down the middle of it, you put it in a triaxial cell, and you then apply, typically you apply no pressure on the boundary and you simply start to apply pressure on the inside wall. Sorry, that's incorrect. Typically you apply no confinement on the inside wall, and what you do is in your triaxial cell, you apply pressure on the boundary. And you keep on applying that pressure until this thing fails, okay? We did this by applying pressure on this thing by using this algorithm whereby we find the particles on the surface, we conceptually construct a chain, based on the pressure and based on the local orientation of this chain, we can apply an external force to those particles. So this is our pressure application procedure. Okay, there was also some tests done with confinement on there. Okay, um, and in that talk, we talk much more in detail about all this stuff. But here's the very, I think, very powerful results here. So what we're doing for this model then is we are going from, uh, we are increasing. What you're going to see is you're going to see an increasing of this outer pressure from 30 MPa, and then you're going to increase it to 30.5, and you're going to watch how the material deforms in response to that and how it begins to form this breakout notch. So if we look at the damage, and these colored things again are fragments that have formed. So if we look at this, notice at this point, so this thing at this point was loaded to 30 megapascals on the outer boundary. And at that point, this is the damage that existed, because this thing doesn't just go from no damage to failure. It slowly progresses in damage as you increase the outside pressure. And so here you're seeing the power of the flat jointing. These cracks are partially broken. These edges, these boundaries are partially broken. These guys are fully broken. Red is tensile breakage, blue is shear breakage. And so at this point, you can see how much this thing is. Now, as we continue to load, or sorry, and now as we apply this load, this from 30 to 30.5, and we watch the system readjust, what we did is we set all the displacements to 0 as a reference, and we just want to look at the deformation and damage that's forming due to this little increment of load. And what you will see is you will see this notch begin to develop, and you're seeing the displacement field begin to develop. And you can see how this notch is dilating inward, and you can see how the displacement field, because this is softer now, the displacement field moves upward. And what you do is you form a very high compressive region up here, and that's what stops the damage from forming. You can see the big dilation, and you can see these regions here. These are these breakages. These are these fragments that are forming. So you're getting these surface parallel fragments that are forming. This, by the way, is a super crude model with very large particles. We of course ran images of particle systems with much smaller particles and got the same type of response at a much higher and better resolution. And I can show you that in that talk if you're interested. But this is a good illustration of the behavior. Now let's look at the same system, but let's look at the force chains. This is the initial system where, and because there is some of this damage here, this material is a little bit less stiff. And so you're beginning to see some arching. Thickness is proportional to magnitude of these force chains. As this material, you're going to see as those cracks happen, this material softens, it redirects the stresses up to into the rock, producing a big region of compression. And as we all know, the more confinement you have on a rock, the stronger it gets. That's why these breakouts are stable. So if we watch this, you're going to see as this starts to break, watch the force chains rearrange in response to that. And look at how it's forming this very high compression region at the tip. As more damage occurs, there's almost no load being carried in this broken material anymore. And again, this is the mechanism as to why you get these borehole breakouts. And also the borehole breakouts have this tendency, they have these surface aligned fractures and fragments that form. And so that's what we're seeing here. Notice at this point, this is almost pretty much fully formed. And now we've got this big compression region at the tip of that notch, which is shutting down the process. So then again, obviously, if we increase the load a little more, this thing can grow. This thing can grow. Eventually, these things fail in a very interesting way. All right. This type of modeling is only going to get better as you have better and better resolution, more and more particles. That means you have to run faster models. we do have the multi-threading is already in there, and it works quite well, and it's totally hidden from you as a user. You don't care. It just automatically works in the background. Um, and we are developing this business to be able to run this on these big clusters of machines. For example, some years back, uh, BP funded ITASCA for a number of years, probably on the order of 800 or more $1,000 to develop to take PFC 3D and make it work for hydraulic fracturing, large scale hydraulic fracturing. And so what was done is we said, okay, build an assembly of PFC 3D particles to begin with, a big giant system, and then we're going to write a whole new code, which is essentially going to take the PFC code and it's going to take out all of the logic that does contact detection. So what you just have is an enormous collection of arbitrarily oriented springs. And the only thing that can happen is those springs can break. And so because of that, it runs like 10 to 20 times faster than PFC because most of the computation in these models is contact detection of new contacts forming. That work then, and so and then there was also, of course, fluid put in there, and so it would track fluid and it would apply fluid pressures, and then you could get this localization where the fluid forms these big fractures and these hydrofracture things. And it also only really makes sense for tensile opening of these springs. If you start having shear grinding and stuff, that's not going to really be handled well because there's no new contacts forming. So we called this a lattice code. It was developed originally for BP by their funding, and they used it. And then probably 2-3 years ago, we reached the point where they said, okay, if you want, you can commercialize this. And so we actually have commercialized that. That's called Excite. And there's probably, I don't know how many, 5-10 people in the world that are using it. As far as I know, they're mostly researchers. And that code Excite then has also been made to run under MPI, and that's very successful. And so the guys at BP are running that Excite on these hydraulic fracturing problems. BP has some enormous giant compute nodes where they have all hundreds of machines, and that's working very well. I don't know, they're getting speed ups of I think like on the order of 20 or 40, and they're building extremely large models. But that took a huge amount of time and funding to do that, and that was much easier to do because it's a fixed lattice of springs. And so once you know that fixed lattice topology, you can, in a reasonable way, pass that off to these different processors and make that work. So I'm just mentioning that as an example that this scheme can be made to work under MPI, and we know how to do it. And we've already done parts of PFC to make it do that, but it's not like, oh, it'll be ready in a year. Probably it almost for sure won't. As we can do faster computational speed, we can also now begin to do these boundary value problems where you have like a local region around a tunnel, just like that stope advancement, right? And we're going to do more and more. Most of the work with these bonded particle models has been looking at like specimen scale things and doing compression tests and doing tension tests and then looking at the effects of different microstructural things. Or some people have built these PFC models and run them through different strain paths, these specimens, and then based on that you can develop a constitutive model to be used in something else. When we start to apply these bonded particle systems to boundary value problems, we start to have these scale effects. We see this in the model, and what do I mean by that? I'll give you the example of what we learned in that perforation damage study. So I'll talk about that thick-walled cylinder test. It's like a bigger scale model in a sense. It's a non-traditional test, let's say. And what you have then is what we found is that we constructed a PFC 2D flat jointed material. We were able to show that we could match the tensile strength and the UCS and the increase of strength with confinement. And we then built like a series of those PFC materials where we had smaller particles and smaller particles and smaller particles, and we were able to show that we got the same UCS and the same tensile strength. And so for those properties, we were independent of particle size. What you find is that if you're doing, for example, a compression test, you need to have a certain minimum number of particles across the diameter. And once you have that many, and that might be 15 to 20, once you have that many, if you add more and more and more, you still get the same answer. So it's like you have to have sort of a representative volume, which is obvious, right? If I'm doing a compression test in 3D on a bunch of bonded particles, if I only have 2 particles across the width, there's not enough resolution in there to have a representative volume. So for the direct tensile strength and the UCS and the triaxial type response, that response is independent of particle size. Then we took that same material then, and we built these thick-walled cylinder models. And what we did is we said, okay, let's build a thick-walled cylinder model with this particle size, and we measure the failure load of that thing. Then we go and we make all the particles half as big, and we measure the failure load, and we make it half as big again. And what we find is the failure load gets smaller as the particle size gets smaller. And so, and you can think of that, well, okay, I'm not going to talk a lot, but that's an example of a size effect that we see. My understanding is that same sort of a size effect is seen in the field. Think of making the particle size smaller. There's 2 ways you can do this. You can keep a fixed thick-walled cylinder opening size and build materials that have smaller and smaller and smaller particles, okay? Or you can take a fixed PFC material particle size and you can do thick-walled cylinders that have bigger and bigger and bigger sizes of diameter. In both cases, the metric that you're interested in is the number of grains, the number of particles across the diameter of the hole. That's like a representative scale. And what we find is that as you get more and more particles across that diameter, it gets weaker. My understanding is the same thing occurs in these perforation in these boreholes, where if you make your borehole bigger and bigger and bigger, it gets weaker and weaker and weaker. So we think we're seeing that same sort of, we are seeing that same sort of effect in here, this size effect that's just naturally occurring. That whole issue is not that well understood. There are some hypotheses I have, and I speculate on that in the paper about this and in that talk, but it's not 100% understood. And so what people typically do, so let's say now we're doing another type of boundary value problem where we have a tunnel and we have high compression stress, and we know that there's going to be some breakout notch, for example, forming in this material. And so what we might do is build a big, huge continuum model, and then in the region of interest where the damage wants to be explored, we're going to put a PFC material in there, right? So the first thing you do is you do lab tests on that PFC material to match the UCS and the direct tension strength and all that. And what you will find if you take that material then and put it into the tunnel, that material will be too strong. And so when we move from the lab scale to the tunnel scale, there has to be some reduction of strength. And so the question is how much reduction? And that's an open question that no one in the world of microstructural modeling has addressed in an adequate way. So that's another, that's an issue. That's what I mean when I'm talking about how to interpret scale effects. And I don't remember what this button is going to do. So let's go see. Oh, and this is no, that's something else. Okay. Wait, is that, yeah, this is actually a discussion of those scale effect things. Since I've already talked about this, let me see what this is here. Let me show you this. This was an example of that system where we built these specimens here. And then we went, and you can see how as we change the particle size, we have this type of resolution on the boundary. That's the boundary. or we have this type of resolution, and this then is showing it's getting weaker as we go. Yeah, we don't need to talk about all that other stuff right now. Okay. And this then is what I would suggest, is that these things should be, we're now starting to do this to say this is a type of representation for a granite, this is a different type of microstructure for a sandstone, etc. Again, you always want to keep these things as simple as possible. You only want to include things, but to do that, you still have to have the relevant micromechanisms, right? If there's a certain thing happening at the micro level, you need to have the model has to be able to also do that. And again, that's the guiding philosophy of this type of modeling. And I'll close with a quote from Einstein. When Einstein was asked what he would have done if his theory of general relativity had not held up, he replied, "Then I would have been sorry for the dear Lord. The theory is correct." So that's the end of this bonded particle model discussion.